Alright, let's look at 340 longest substring with at most k distinct characters. Just reading the title here, we are looking at some kind of a substring within a string, which is basically a window within the string. So we're looking at some kind of a sliding window techniques that be applied to this question. And we're asking some information statistics about the uniqueness, number of unique characters within the window. So we could probably gonna use some kind of hash map to store the information about each characters inside the window. So that's just by reading the title here, it suggests us it's gonna be hash map plus sliding window. So read the question here. Given a string, we need to find the length of the longest substring such that it contains at the most k distinct characters. So just looking at the example, we have ECEBA. The longest window is at the most 2 distinct characters is ECE here. So it contains E and C, and the length for that substring is 3, so that's the longest one. And the second example, it's the whole string is just consists of one character A, and we're asking for the longest substring with at the most 1 character, which is just repeating the longest repeating character within the string, so it's the string itself. So these 2 examples isn't particularly interesting. I guess it's quite straightforward about this question. So let's code a inefficient, relatively inefficient algorithm first, and then try to improve that. So a relatively inefficient algorithm is to keep a sliding window indicated by the left location and right location for the window, and we try to expand the window to the right by ingesting the frequency count for the character that's coming in, by incrementing. If it's already in there, we increment. If it's not there, we create a new entry. Once the window exceeded the length of k, we try to shrink the window from the left side and just try to pop out, throw out 1 character at a time, and increment the L location. So this algorithm is relatively inefficient, but we're gonna code that up and try to optimize from there. So the so that's let's start code that solution up, and then try to improve from there. So as usual, we handle some kind of edge cases because it's not mentioned whether the string or k can be empty or not. So handle it here. So we're gonna iterate over the string once with a right pointer with a variable r to indicate the ending, the right boundary for the window. And we're gonna try to update the window by the newly ingested character. We're gonna use the window to keep track of the number of times the certain character appeared inside the window. That's the most naive way of maintaining the full information about the relatively, actually more than necessary, the information we need about the window. So we're gonna get char default 0 plus 1. So the window is it's a regular dictionary in Python. So that's we expand the window to the right by 1 character. We update the statistics about the character frequency inside the window here, and then we try to determine whether we need to shrink the window or not. Is greater than k, then we will decrement the leftmost character's frequency inside the window. So it's literally just to throw out that character from the window. And if the character's frequency drop to 0, meaning that the window size will just go down by 1 to become k again, then we should stop. So we need to, for the termination to work, we need to actually erase this character if its frequency becomes 0. So after we maintain the unique number of distinct characters within this window, we can do an update to some kind of variable that keeps track of the maximum length for the window at any given time. And the L initially will be 0. So yeah, at the beginning the window is just one character with left and right being the same location. And since in the beginning just one character, the size can be the two variables left and right, they are both 0, but the length of the window is 1, so it's right minus left plus 1. So that's pretty much the code. Let me quickly check if I have problems. We do a for loop here. So this outer loop is definitely in linear, but the costly part is here. This can potentially be ON as well. That's the worst case when when everything is kind of equally distributed, but only in the very end or towards the very end it becomes to blow up. So you have to try to decrement the frequency count for the characters relatively evenly until very end. You begin to able to decrement the window size. So that's the worst case. So it's kind of a squared time, but that's the very worst case. If that string is regular, the character's frequency in there is kind of a randomly, I guess this is not too bad. So I think this should be the first very naive kind of implementation. The space complexity, it's just based on the number of unique characters in there. So it's in the worst case, it's order of the window size is k. So the key number of keys in here is at the most k plus 1. So the space complexity is order of k, but the time it's I guess it's squared in worst case. So let's submit this. It's not working. Okay. It's a small k. Gee. Let's see now. Yep, this time it's working. Not too bad. So then we'll begin try to think how we can cut down the time in this step. We want to know the else location, right? That's being finally used to do the update of the window. So actually, instead of storing the frequency count of every character and decrement that by shrinking the window from the left when we exceed the uniqueness of characters in there, we can actually just remember the last location. The last location for every character inside the window, so that if we want to shrink the window, we pick the character that's with the smallest last seen location. Then we can just directly go there, directly move L left to there and do this updates. So now the window will be storing the character to its last location rather than the frequency count here in the first naive solution. So let's just do some really quick modification to get to make that happen. So instead of the frequency count, we will just store the last location for the character. You know what? Let's actually comment this whole chunk here. Yeah. So window character is equal to the right location, and if the length of a window, if the number of unique characters inside the window is greater than k, then we do a linear search for all the keys, all the key value pairs, and find the minimum value inside there. So that's the earliest location, earliest last seen location for a character inside the window. And we're just gonna pop that out. So so instead of increment this L, gradually one by one, we directly jumped into the location. And for this to work, we're actually gonna drop the +1. Let's put it there. And the L will be started with -1 there as well. Yeah, the reason being that in the above code we have L +1 after the while loop, so it's the L is the first inclusive one, but here L is the location before the first included one inside the window. So it's literally the one that we throw out that's outside the window to the left. So we don't need to +1 in the update here, and for that reason we also change L to -1. So yeah, so I think I should comment more things to keep the both solutions in the same code editor, so that we can do a comparison. So that's the common part is the squared naive frequency count solution. What we have currently here is the improved solution. So the complexity is being reduced from order of n to order of k here. For that, we need to find the minimum value, and we have k items, key value pairs in this window. So that's order of k instead of order of n. And so that's a reduction in terms of time complexity. For the space, it's still the same. So let's try see if this works. Okay, we got some nice improvement on this. So I guess we can still improve upon this. For that, this scan here, it's unnecessarily more complex. So if you did the LRU cache solution question, you know that there's this ordered dictionary or linked hash map kind of data structure that can give you constant access to a constant time operation to do insert and get, and it also maintains the natural. It allows you to move a key value pair towards the end. Basically that's I'm gonna put a link to that LRU cache problem here. Basically, you want to maintain the ordering of how when the key is inserted here, so that we don't need to do a linear scan of the key value pairs to find the minimum key. Basically the key value pairs are going to be stored in a double linked list. When we do an update, we'll pull that key value pair towards the tail. So when we do insert or update, we're gonna basically move that key value pair towards the end of the doubly linked list. And when we're gonna pop, we just directly pop the head element, which is the least recently used. So it's gonna have the smallest location. So let's use that to. If we use that data structure, we're gonna reduce the order of k in search for that last location to 1. We know that the head element, the head node, the head key value pair is the one that we want to get rid of. So yeah, so let's comment this out and just code that up. So instead of the regular dictionary, we're gonna have a order dictionary from Python. Order dictionary, and everything else for this is still out of n. We're gonna do windows.char. It's the same. We keep track of the last location, but one extra step we need to do is to actually grab that key value pair, the node for the key value pair inside the doubly linked list, and move that towards the tail. So it's so that just by the node sequence and node ordering inside the doubly links, that we know which one is going to be the one we need to pop out later on. So we move it to the end, and then there's this condition check here. If the window has exceeded the number of distinct characters here, we're just gonna directly we're popping the head elements, the head node. So that it's the key value pair. So we don't care about the character. We only care about the location that we previously inserted there. So pop item, okay. Pop item first, last. We wanted the first. We want to pop the first one. So we set last equal to false here, and after that we can do the update. So that's pretty much the code with order dictionary. It's pretty much the same with here, except when we need to pop, we don't need to do a scan to find the minimum. We just know that it's gonna be the very first one. But one thing we need to do is to, after we insert or update the value for the key for the character, the last location for the character inside the window, we also need to move that towards the end to maintain that ordering. So that should work. Let me submit this. Okay. Yeah, it's pretty similar to this location here, this solution here in terms of actual submitted runtime. But in theory, this is faster because this is constant. So yeah, that's the question 340. Okay.